Hello, everyone, and welcome to another class of ATMO 412. This is week, 1,000 of the quarantine, or at least that's what it feels like right now. I hope you guys are doing well. I hope you're staying healthy, both physically but also mentally, which is equally important. I have been well physically. I've been well mentally as well, although I have to say that my house feels more and more like the Overlook Hotel, if you get the reference. I've been alone most of my life, and I thought that I was very well prepared for isolation and quarantine, but boy, oh boy. It's been a bit harder than I thought it would be. But anyway, I'm hanging in there, and I hope you are too. If you need anything, if you want to talk to someone, if you are running short on pasta or food or toilet paper, as usual, please do not hesitate and get in touch, either with me or with any other faculty. So, this having said, we can start with today's lecture, which is a little bit more equatorward than the other lectures, as today we will talk about the tropics. So if you look at the syllabus, you'll see that today we were supposed to have the wonderful Bob Ballard talk to us about Hawaii weather. Unfortunately, quarantine made everything really challenging, and so unfortunately for all of us, Bob will not be teaching us about Hawaii weather. But I thought it would be nice to think about the tropics a little bit. After all, this class is about meteorology in general, and although the main focus was really sort of synoptic scale meteorology, I think it's good to know the kind of weather that we also have in the tropics. Now, obviously, a complete discussion of tropical weather would be way, way too long. And I encourage everyone to take ATMO 416 next year if you are interested. And so for today, I just picked one single topic which I am really interested in, which I find really interesting, which is severe weather in the tropics. Now, why do I find this interesting? Well, for a variety of reasons. The first reason is that I am generally interested. This will not be all about me. I just want to provide some motivation why I should pay attention. But this is not going to be like, me talking about myself because I don't have any friends. So I think severe weather is just interesting from a physical point of view because, well, there's so much we don't understand about severe weather. It's really hard to study it from a modeling perspective. It's hard to observe severe weather. It's kind of beautiful to look at. Like if you think about pictures of supercell storms, which, okay, they happen on the mainland, but we're thinking severe weather now. Or pictures of hurricanes, which are absolutely horrible dynamical systems and that we're all afraid of. But they're also kind of pretty, if you like nature. They're pretty in a morbid way, if it makes sense. And so I feel this fascination for severe weather. Obviously, severe weather, there's no need to motivate why we should study severe weather as scientists, given all the damages that it can cause. Now, in the tropics, there are a couple of myths when it comes to severe weather. The first one is that, the only really severe weather event that happens in the tropics is tropical cyclones. As I said a few minutes ago, to talk about the tropical weather more generally, and so to talk in depth about tropical cyclones would take far too long to do in one class. And so let's just ignore tropical cyclones for a bit, okay? But if you take out tropical cyclones, there is this myth that there really isn't much else. what else happens in the tropics. And part of this myth is real in the sense that there are less severe weather events in the tropics compared to other places in the mid-latitudes. There certainly are less severe storms in the tropics than there are in Oklahoma. That's for sure. Less tornadoes in the Pacific than there are in Oklahoma. At least big tornadoes, EF2 plus tornadoes. That's a fair statement. But also, that doesn't mean that there is no severe weather at all. One thing that we have to pay attention to when we think about severe weather in the tropics is that, well, a lot of the tropics is ocean, and it's really hard to observe the ocean, which is why little was known about hurricanes before people invented satellites. At least little was known in terms of how many hurricanes happen every year. I don't want to get too philosophical, but if a hurricane happens in the middle of the Pacific Ocean and there's nobody there to observe it, there's no, it's far away from Micronesia, from Polynesian islands, from any kind of land, didn't really happen. Now, hurricanes are pretty big, as we all know, and so now we see them with satellites. Severe local storms and severe weather, it's a little bit more challenging because you can't see a tornado from the satellite. So how do you know how many tornadoes there are every year over the Pacific? It's hard enough to count them on the mainland because you need someone to actually see these tornadoes because they're small. How do you do it here in the ocean? You can count them. You can count waterspouts and funnel clouds in Hawaii, provided that they're close enough to the coast. But if you can't see them and they're far from the radar, then it's kind of, it's almost impossible to recognize one. And so I just thought it would be interesting to think about severe weather in the tropics and talk about them a little bit more. As we said, hurricanes are the poster child for severe tropical weather or tropical severe weather. I don't know. Well, any combination of these words. But we're not going to have enough time to talk about hurricanes. So, if you're interested, Forward 16 will be offered next year. Or I'm happy to talk to you over Zoom anytime about hurricanes. What we will talk about today are 4 categories of severe weather that happen in the tropics. More common than we understand, than we realize they are. They're not necessarily Hawaii-based. They're not necessarily subtropics-based. They're not necessarily ocean-based. And these categories that we'll talk about today are hail, straight-line winds, tornadoes and waterspouts, and dust storms. The last category is clearly not an ocean-based phenomenon. So let's start with straight-line winds. Now, straight-line winds, what we mean by straight-line winds, it's basically winds at the surface that exceed a certain threshold. You could imagine that, as we often said throughout this class, setting a threshold for these phenomena is kind of arbitrary in a way. 25 meters per second seems to be a decent value to recognize winds that can bring a considerable amount of damage. So 25 meters per second is about 75, well, it's about 100 kilometers an hour, so it's about 60 miles an hour. Wait. Was that correct? Wow, I can't do math anymore. See, this is what happens when you're stuck at home for too long. Can't do math. So, I think it should be correct. Anyway, So one of the causes for these straight line, but do the math and tell me if this was not correct. Yeah. Anyway, well, these can often happen, for example, caused by extratropical waves. So, we talked about troughs and ridges, sort of long, sort of large waves that happen in the flow. The example that is reported here in the figure that you can see on the slide, you can see that there's a trough that is digging through all the way to Mexico, and there's a low pressure system centered to the south of Alabama and Louisiana, I want to say, so to the south of the Gulf states. We are looking at sea level pressure, okay? So notice that in front of this, and we will see some better pictures later. But in front of this, this is obviously there's obviously a cold front that is approaching Cuba and Florida, and this approaching cold front causes essentially a squall, we call a prefrontal squall, that on a particular day in 1993 produced straight line winds at speeds that were greater than 55 meters per second. Okay. This was a bit of an exceptional phenomenon, and the sort of the parent cyclone that caused this was one of the strongest that had happened in the previous 40 years. So this is a bit of an exception, but it's not an uncommon situation that you could have systems that can come all the way down, and they can cause before the cold front sweeps through, there can be severe straight line winds at the surface. This is another image where we are seeing now the isotachs. Isotachs are lines that join points that are characterized by the same wind speeds. Okay, and the isotachs in this case are represented by dashed lines, and the values are not given in meters per second, but they're given in knots. So you can see that between Florida and Cuba, we have something like 90 knots, and we have about 70 knots winds, 70 knot winds over Cuba, which is quite considerable. This is another picture essentially of this event, and this is representing wind barbs essentially over Cuba. It kind of tells the same story. Now, obviously, the Gulf is one region where these things can happen, and typically, these events happen whenever there is a low pressure system that can come all the way down. When the conditions are ripe, it can cause these straight line winds. But this is not the only type of situation, the only area of the world where you can have straight line winds that specifically exceed this threshold. So India and Bangladesh, and the northwestern India and Bangladesh are also regions that are prone to having these. Sometimes people talk about nor'westers, which is kind of funny if you lived on the East Coast. And these ones have, we've seen surface outflows that have speeds of 39, 40 meters per second. Now, surface outflow is another word for straight line wind. Essentially, what is happening is that, remember when we talked about convection, often you have these convective events, and these convective events generate downdrafts, and the downdrafts are currents of really cold and dry air that descends all the way down to the surface. And when the downdraft is particularly cold for whatever reason. Maybe it originates in the upper troposphere, or maybe there's so much rain evaporation that happens in the downdraft that it gets super, super cold. When it reaches the surface, then it expands out, and it does so typically at a very, very high speed. Okay. Well, it can do at a very high speed, and this is what causes these straight line winds. Because of this phenomenon, because these winds are essentially due to the cold pool, if you will. Surface outflow is another. Outflow or storm outflow are other words that are often used. In these cases. Another region where we can have straight line winds of particularly great speed is South America. Now, South America, if you think about South America covers a pretty big portion of the planet. I think we can all agree. But there is a part of South America that isn't really south at all. And there's a part that is close to the equator. But I suppose we are adhering to the sort of the colonial nomenclature that, everything southward of Great Britain is south something, I suppose. So there's portions of South America, like, for example, the Amazon, that are in the deep tropics. And in the deep tropics, what happens is that typically you don't have a whole lot of synoptic forcing. There, whenever you have temperature gradients, horizontal temperature gradients that are useful in the mid-latitudes for creating extratropical cyclones, well, close to the equator, the atmosphere can actually generate waves, gravity waves that sort of propagate away the temperature anomaly. And so as a result, all these troughs and ridges that we've seen so far don't really happen in the tropics. We in Hawaii feel them sometimes during the winter when the Hadley circulation moves southward a little bit. But in general, if you are close enough to the equator, so anywhere between 10 north and 10 south, it's really hard that you'll get extratropical cyclones. Obviously, you cannot have extratropical cyclones in the tropics. That would be a bit of an oxymoron, but there is a reason why extratropical cyclones, they're called extratropical and don't happen in the tropics, okay? And so what you tend to have in the tropics, and particularly in these areas close to the equator, let me drink a little bit, you tend to have waves, easterly or westerly waves that propagate. You can have Kelvin waves, Rossby waves, all kinds of things that propagate in sort of the deep tropical regions. And these waves sometimes can generate convective systems, mesoscale convective systems. So they can generate squall lines. And so even though we are far away from the environments that are so conducive to squall lines and severe weather events at the mesoscale, like the Great Plains, you can still have these kinds of events even in the deep tropics. So VIMAX was a campaign that happened many years ago, and if I'm not mistaken, it took place in Venezuela, and that's the V in VIMAX stands for Venezuela. And, well, this campaign observed a decent amount of squall lines. Recently, in 2014 and 2015, a massive campaign was organized in the Amazon called Go Amazon. And they too observed a number of mesoscale convective systems that were pretty intense, even though the Cape doesn't get to be as large as the mid-latitudes, where, often you have 5,000 joules per kilograms or something in Oklahoma. You can still have, even with modest Cape and some wind shear, you can still have decent squall lines that would propagate and generate, substantial outflows. In the South America, so if we go all the way down to Patagonia, things are a little bit complicated. There can be sometimes that can be in Argentina. That can be supercell storms. A campaign called Relámpago recently took place to study these storms, but other things like squall lines and straight line winds are not as common as in other regions. Now, another big region where squall lines of considerable intensity, and so straight line winds as a result, can happen is Africa. In Africa, you can have a similar sort of a similar latitude, and in particular, there can be, we don't have time to get into this, but the heat of the Sahara, essentially, and the contrast between the heat of the Sahara and equatorial Africa generates a jet. And this jet can create easterly moving waves. And these are known as African easterly waves. You may have heard of them. If you know anything about hurricanes, you may have heard of African easterly waves, because sometimes these are associated to tropical cyclogenesis. So essentially, these waves are traveling over Africa, and when they leave the continent of Africa, they create some vorticity, and vorticity plus really warm surface temperatures and low wind shear, yada yada yada, can be conducive to hurricanes in the Atlantic. Okay, well, but African easterly waves are they can also just simply generate squall lines that are responsible for straight line winds. Okay, this we would be talking about. If you want to place these events sort of geographically, we'd be talking about southern part of the Sahara and a region in Africa between 5 and 10 north, more or less, that is known as the Sahel. Sahel is an extremely important region for the interaction between the land and the atmosphere, and it's a semi-arid region, so it's not as lush and green as equatorial Africa, but is also not as terribly dry as the Sahara Desert. It does feel the influence of the African monsoon, of the African easterly jet, which is caused by the Sahara Desert. And so often there can be pretty decent squall lines. Sometimes these are associated also with dust storms, because if the squall line and the outflow, we'll talk about this later, but if the outflow travels over a region that has a lot of sand, well, you can imagine that the outflow is just going to pick up the sand and move it along. So sometimes you can see these dramatic images, even from the satellites, where you can see these plumes, these beautiful plumes of sand that are moved about by these very large systems. So the figure here is just showing pictures of. These are essentially different snapshots of a system that was moving, sort of a squall line system. This is radar. The black is anything above 50 dBz, and the words are failing me. Sort of grayish contours. These are between 40 and 50 dBz. Okay. This is essentially a similar image, but we're showing you these squall lines not from above, but from the side. You can recognize, if you revise what we talked about when we were discussing squall lines, you can basically recognize the main ingredients, the main systems, the main ingredients for the squall line. The difference here is that there are these easterly waves that generate squall lines, and so squall lines are moving westward. The squall lines on the mid-latitudes, on the mainland, for example, they're moving eastward. And so it would be the same image, but flipped. Okay, so to the left, a distance about 10 kilometers from the nose, you have high precipitation and you have the deep convective part. And then to the right, you have the trailing stratiform region. After about 100 kilometers, you have sort of the secondary maximum of reflectivity and precipitation. As we mentioned, India is also a place that is that can have straight line winds. These are often associated with monsoonal systems. Sometimes there are there are events that happen before the sort of the pre-monsoonal period, and so there are sometimes sort of high thunder frequency before the pre-monsoon period, but these times typically have no severe wind or hail. It's usually when the monsoons are sort of started that we can observe these kinds of events. Southern India don't have as many events. The next phenomenon that we want to talk about that is, I feel it's a bit like the underappreciated, don't want to use the word hero, but sort of it's a very underappreciated phenomenon, severe weather event, and it's hail. Now, it's obviously less dramatic than tornadoes. I'll give you that. But still, it can cause significant damage. Like if you imagine a big swath of land that is hit by really large hail, and suppose that this happens in a place where a lot of crops are growing, then you're going to have considerable economic damage, and maybe a bit of a famine because of the destruction of the crop. Property is obviously at risk. I remember driving, being caught in a hailstorm one night. Now, I don't live in the tropics, and I live in a place that, I didn't live in the tropics. I live in the tropics now, but I didn't live in the tropics. I didn't grow up in the tropics. I grew up in a place that during summertime, hailstorms, or used to have hailstorms. And I remember one night I got caught in a terrible hailstorm, and even though I obviously didn't lose my life, but the car that I was driving was completely dented, like any surface. I couldn't find, anywhere, any what's the English word? Any shelter where I could, go underneath. There were trees, but even though I was still a string theorist, I knew enough about storms to not to go under a tree during a storm. But yeah, so I had to take the car to the mechanic, and it was, some thousands of euros to get it fixed. So even though I didn't get, I didn't get teleported to the land of Oz by a tornado, still, it was considerable damage. And so hail is often underappreciated, but I think it's really important, and it's a very challenging weather phenomenon. It's extremely hard to study with numerical models, and very few things are. Well, it's a less known atmospheric phenomenon than others, shall we say? I would argue. And even though you would imagine that hail would be prevalent in the mid-latitudes, and there certainly are a lot of places in the mid-latitudes that get a lot of hail, a lot of considerable amounts of hail, there are places in the tropics that have also a lot of hail. So if you look at the table that I'm showing here, this is a sort of it's showing the counts of hail events over a certain period of time in different parts of the world, different columns referring to different radii for the hailstones. We have less than a centimeter, which is not great. It's not big, but still, it's not great to be hit on your head. Between 1 and 3 centimeters. 3 centimeters is a little more than an inch. And then third column is more than 3 centimeters, which hurts a lot if you get hit on your head. And you can see that there are some places that are kind of unsurprising. Oklahoma has pretty large count. Illinois also. New England, although I was a little bit surprised to see New England because, I lived there for a while. I know it's a big region, but I never saw hail, to be honest. But also, you have areas where you wouldn't have necessarily expected that. Kenya, for example, has a higher frequency of small hail than any other place. Sort of the medium-sized hail, Colorado seems to have a decent amount. Denver area also has considerable amount. Less, obviously, in Kenya, but northern India, for example, has quite a bit of hail. And if you then look for large hailstones, Oklahoma, southwestern France, for some reason, has a lot, but northern India seems to have a lot of hail. And in fact, northern India seems to have most severe hail compared to other location. Kenya, which I wouldn't have thought initially, although it doesn't have as much large hail, it does have quite a bit of smaller hailstones. Now, why is that? Well, let's look at a map of Africa, for example, and the map in the background, sort of in the top right, this is showing frequency of hail over Africa. And the map to the southwest, it's showing topography of Africa. Now, notice, obviously, in the subtropical regions to the very north, i.e. the Sahara Desert, there aren't a lot of hailstorms because, well, it's the Sahara Desert, and so there isn't a whole lot of moisture to begin with, as you might have guessed. But if you look at places like, where Kenya is, or sort of in the Ethiopia, Eritrea region, there is considerable amount of hail, but there's also significant topography. We move to another region and we look at India, for example. Look at sort of northeastern India where you have a lot of hail. Well, it's very close to the Tibetan Plateau, which in the figure in the bottom left is that grayish, enormous area that looks a little bit like a whale. And that is also where you have significant topography. It's, I guess, a posteriori, it's kind of intuitive that you would expect a relationship between topography and hail. So just think about what happens in a thunderstorm, right? You have updrafts that are, bringing up a lot of air. Sometimes these updrafts can be really severe and really, really strong. Thunderstorms above a certain height essentially are in sub-freezing conditions. And so they are, at the very least, in mixed phase conditions. The top of the thunderstorm is typically made of ice. They're completely in the ice phase. And so there, you'd probably accumulate a lot of hydrometeors in the ice phase. Now, if you were in Kenya with no elevation, temperatures in Kenya are really high. And so you have this hailstone, 1 centimeter in diameter, hailstone, it's coming down. Well, because the temperatures are so high, by the time it reaches the surface, it's probably melted. However, if you have a really high mountain that kind of intercepts the hydrometeor as it's falling down, well, this hydrometeor just has no chance to melt. And so that's why when you have significant topography, it's not surprising that you'd expect that you'd expect things like hail, even in places where you wouldn't expect something like that, like India or Kenya. Okay, now I guess I'm going to guess that these are probably everybody's favorite just because, well, tornadoes are just spectacular. I'm not their biggest fan, let's say. But yeah, they're kind of spectacular, so they always capture everybody's attention. If you ask me, I don't know, they're kind of a redundant appendix to some otherwise beautiful dynamical systems. The storms that often generate tornadoes in the mid-latitudes, these would mostly be supercell storms. And these are beautiful storms. Absolutely amazing dynamical systems with very complicated dynamics. And so they're super fun to study and to analyze. Tornadoes don't really do much. Yeah, sure. They destroy houses and cities and kill people. So, that's why we should be able to forecast them better. But from a purely physical point of view, they don't do really all that much. So I often feel that tornadoes are, kind of overappreciated. Their importance is not overstated, though, because this detail that I mentioned in passing, that they destroy cities and kill people, it's not a little detail. This is super important, and it's why we should continue to study them. I think from a purely aesthetical perspective, I'm more fascinated by their parent storms than others. Now, obviously, yes, sure, Oklahoma, the Tornado Alley, as the name may suggest, is the place that gets most tornadoes in the U.S. and in the world. And so, compared to Oklahoma, the tropics don't really have an awful lot of tornadoes. Argentina has a lot of tornadoes, and everybody else is kind of far away. But still, tornadoes are a significant enough threat, and still our forecasting abilities are so poor that we should really be able to understand tornadoes a bit more. Okay. On the mid-latitudes, the biggest responsible for tornadoes are supercell thunderstorms. I don't want to give you a wrong number, but I think it's definitely more than 70%, maybe even more than 80% of tornadoes in the U.S. are generated by supercells. However, only about 20 to 30% of supercells generate tornadoes. Okay. In the tropics, we don't really have supercells. And the tornadoes never get to be as strong as they are in the U.S. And so in the Fujita scale, or the enhanced Fujita scale, they very rarely are worse than EF1, which, still not great to be in one. If you're wondering, the distinction between waterspouts and tornadoes is that waterspouts are over water and tornadoes are over land. And so let's assume this is hopefully a very remote hypothetical. Let's assume that there's a waterspout offshore of Oahu. If this waterspout makes landfall, then it would be technically counted as a tornado. Okay. So the figure here is a very old figure, but still pretty accurate. And it shows, well, at least for the U.S., it shows where tornadoes happen around the world. There's the dark region in the U.S. on the mainland, and this is where the Tornado Alley is. And, well, yeah, if you hadn't guessed it already, there's a reason why it's called the Tornado Alley. Argentina, that we see. Australia actually has a decent amount of tornadoes. Japan has some tornadoes. India so in the northeastern part, has some tornadoes. Now, so why this would be an entire class altogether, but why are there so many tornadoes on the mainland in the US? Well, tornadoes, as we said, are mostly caused on the mainland by supercells. And supercells essentially need two ingredients. The first ingredient is a lot of heat. And so they require large amounts of CAPE. And the second thing they need strong wind shear. The CAPE is often achieved during summertime when there isn't really a whole lot of synoptic variability. The skies are clear. It's a nice clear day. You accumulate a lot of CAPE. CAPE values often are about 5,000 joules per kilogram. They're not so uncommon. There's also a strong convective inhibition. Sometimes it can be hundreds of joules per kilogram. And this convective inhibition, as the name suggests, prevents convection from deep convection from happening, from exploding out, but also it means that it helps accumulate potential energy. It's like when you put one of those, what do you call those pots that you close, those steam pots, the pressure cooker, because it's a pressure cooker, you can raise the temperature a lot and nothing happens because it's a pressure cooker and it keeps everything together. So you can achieve insane pressures inside of the cooker. But if for whatever reason, the things that keep the pressure cooker together become loose or break, then the pressure cooker will explode like a bomb. And precisely for this reason, because you allowed for a lot of potential energy to accumulate. Okay? So these are two important factors. If you think about regions like the maritime continent or the Amazon, there typically you don't have a lot of convective inhibition. So that could be one of the reasons. Even though it's not completely understood to date why there aren't as many tornadoes. I apologize if I'm a little distracted, but there are a lot of children outside, and it's really hard to focus when there's like 10 people screaming from the top of their lungs as they're playing. Sorry. I am a little bit sensitive to noise. This I knew of myself, but now it's really clear that I am a little sensitive, but also, it's not easy. But, Okay. And also, on the mainland, you have a combination of things. So you have the Cape, but also often you have these sort of a low-level jet that goes from the Gulf and tracks northward. It brings the moisture from the Gulf inland, while at the top you have a flow that is predominantly westerly. So you have westerly flow, you have a low-level jet that is bringing in moisture, and so you have considerable wind shear brought together by the jet, and also there's a change in direction because the flow in the mid-troposphere and high troposphere is typically westerly. So these are perfect conditions for supercells. In other regions, it's not entirely clear why other regions are not as rich in tornadoes. Fortunately, I suppose you'd say. The Amazon, we said, well, it's one of the regions where you would have a lot of moisture and so a lot of potential for thunderstorm, but it's unclear why storms there never get to be as strong as supercells on the mainland. Maybe you don't have this low-level jet that is bringing moisture from the ocean. Maybe it's kind of lost as it travels. Who knows? Australia, as we said, also have a lot of tornadoes. What is interesting is that they're mostly coastal. There's very little inland, and they're mostly coastal. And I've seen pictures of supercells happening over the ocean, and assuming they're not fake, and they could be because it's the internet, stupid. They're quite spectacular to see. There can be tornadoes in India. These typically happen in the pre-monsoon season. And let me drink a little. And typically these are given by thunderstorms ahead of a trough when there is also strong low-level wind. And these can cause significant storms that could eventually generate tornadoes. One of the things that make tornadoes particularly bad in India is that, instead of that region, India, Bangladesh, where they happen, is not that they're so particularly severe. So, it's not like, EF5 tornadoes that last for days, but often they happen in cities that have many inhabitants. And so it could kill a significant number of people just because of that. And as we said, also in Australia, there can be decent amounts of tornadoes. Obviously, if you start to go down in the mid latitudes, then you can have greater potential for tornadoes. In the tropics, they're not as significant, but could still happen. Over the ocean, it's kind of hard to tell, to be completely honest, because as we were saying before, if a tornado happens in the middle of the Pacific and there's nobody, now there was a bird that was trying to come in, but okay. You can see my concentration is, there are good days and bad days, I guess, to keep focus. This is not a great day. It's turning out. Anyway, over the Pacific Ocean, if a tornado happens and nobody's there to see it, how can you tell that it's really happening? And so it's harder to know when and where a tornado happens if you don't have a thick network to measure them. And this is a problem that is common to all kinds of severe weather events. I mean, it's common to tornadoes, and not only in the tropics. If a tornado happens on the mainland and nobody's there to see it, it's really, really hard to know that a tornado is happening. You need forecasters to be watching that area with a radar and catching on it. And even that is not trivial. Sometimes there are radars that have shadows. They can't see if there's like significant topography and whatnot. It's unclear that the count of tornadoes in Europe is accurate because, in Europe there isn't a network of observations that is as thick and as well prepared, particularly in some regions, as in the U.S. this also applies to people who talk about projections of tornadoes, tornadoes and climate change and stuff like that. If you compare the statistics of tornadoes nowadays with tornadoes 100 years ago, you may get the impression that nowadays we have 10 times, 100 times more tornadoes than we had 100 years ago. But then again, 100 years ago, there weren't as many people living in all the places. There wasn't this kind of awareness of tornadoes. And so the fact that they weren't reported doesn't actually mean that they didn't really happen. And because tornadoes don't leave a mark that lasts for centuries, it's kind of hard to tell. It's great in places like Hawaii, for example, where you have such a thick and rich database of newspapers. Maybe you could go through the newspapers and see how many waterspouts were reported. But in other places where people were not as careful or as keen to keep a record, it may be harder to keep track of them. Well, since we mentioned Hawaii, what about tornadoes in Hawaii? Actually, as you may or may not have realized by now, tornadoes are relatively common in Hawaii, particularly during the winter. During the summer it's kind of harder because typical summer weather has, the high to the northeast of us that's pretty strong, it's pretty consistent. And so we have trade wind flow. Trade winds don't really make tornadoes. Luckily, I would add. The figures here are figures from some old papers, which really are the only references that I could find actually for tornadoes in Hawaii. And you can see that for the period examined, which is from 1961 to 1975, there is actually quite a decent count in the Pearl Harbor region. Is there a reason why tornadoes seem to prefer Pearl Harbor compared to the North Shore? Well, maybe it's something to do with topography, but also I would argue that near Pearl Harbor, which is a really hard word for me to pronounce, there's the airport, and so there's more people that are ready to observe whatever is happening. So, maybe if a tornado happened to the north of the North Shore, maybe it would be really hard to observe it just because there wouldn't be anyone there to see it, or maybe it wouldn't get reported. But near the airport, it would be a lot easier to spot one and to report them. And you can see obviously the counts. If you look at the other islands, these are super old pictures, but again, very little has been done on tornadoes and waterspouts. You can see that there are some counts near where the radars used to be, and where the radars are still today. Bob Ballard would have been a fantastic person to talk about this because his master thesis was precisely on this. So as we said, they are more common, however, during the winter. And during the winter, essentially, we can have troughs that are digging in, and sometimes we have cutoff lows that are coming through. All these troughs and lows that come down, what they do is essentially erode the inversion. So there's no trade winds, there's no inversion anymore, and so we have the possibility of heavy rainfall, as we are all aware, and also of tornadoes. Now, we don't have the time to get into this, but the reasons why we have the mechanisms that drive tornadoes in Hawaii are different from the mechanisms that drive tornadoes in the mid-latitudes. Here, it's extremely rare to have supercells. We don't have the right amount of shear. We'd never get the right amount of cape to get like a big, thick supercell. And so mechanisms to explain why supercells develop tornadoes are still debated. It's related to the vorticity and the downdrafts, more or less. here it's more to do with the fact that when the thunderstorms rain out and they generate the cold pools, sometimes these cold pools can kind of play around with the vorticity in the environment, and a really strong cold pool can give a big sort of kick to the air at the surface and increase the vorticity to the point that the vortex sheet is close enough to some ascending air, it gets stretched out and it makes this beautiful tornado. Okay, so the mechanism is not strictly speaking the same one. Still, though, I mean, doesn't mean that they're still bona fide tornadoes and waterspouts, right? These are some stats for the tornadoes. Obviously, interannual variability that we can see here. If you notice, the 70s seem to be 70s and the 90s seem to be pretty good years for tornadoes. The 80s, not so much. Very little is known about what drives the seasonal variability. Well, sorry, not seasonal. Interannual variability, decadal variability of tornadoes. I would bet some money that it's likely something to do with ENSO, for example, and that ENSO affects cold fronts, the intensity and the extent of cold fronts passing by. So La Nina years have certain types of cold fronts, El Nino years certain types of cold fronts. So if instead of focusing on Hawaii, you were to look at the entire Pacific, maybe you'd see that the tornadoes or waterspouts, one year that would happen more towards Hawaii and close to us, and some years that would happen to the north of us. And so we wouldn't see them. And so we would say, okay, no tornadoes in Hawaii. But it's not like... Wow. Can you hear them? Like, I'm always concerned that, it's not like, it doesn't sound like a man house. I hope that this is not distracting for you guys. In terms of the months, as we said, this is some stats that were collected from 1976 to 1997. Notice that July seems to be particularly devoid of tornadoes, although it does look a little bit suspicious that there's this sudden dip. But as you might expect, the months from January to March are the months where tornadoes are really sort of the most common. Summer months, not so much. Now, Florida is not strictly speaking in the tropics, but it's close enough that it experiences a lot of tropical weather, tropical-like weather. And so waterspouts in Florida are very common. And probably Florida, I would say, it's the place in the U.S. that has the most waterspouts. So way more than Hawaii. And this is something that you would have to pay attention to if you wanted to go and be a forecaster in Florida. One thing that is often, not that is often, that I often sort of didn't consider or like whose importance I never thought about until I moved here, is that tropical cyclones often generate tornadoes. And I remember when I moved here, I think about a week after I moved here, Hurricane Lane came, which is quite terrifying, as someone who's lived in like the mid latitudes for all my life. I didn't even have a house yet, and suddenly there was like a Category 5 hurricane coming our way. And one thing that I heard people say that really frightened me was that, also we could have tornadoes on top of a hurricane, which was quite scary. Now, hurricanes are places where sort of intense convection happens. outside of the sort of the inner core, the main rain band, you have many secondary rain bands. And these secondary rain bands, in many respects, they look like squall lines. So you have really strong convection. And you have wind shear, you can have wind shear, you can have really strong convection. And so it's not uncommon to actually see tornadoes happen in tropical cyclones. So this is something that you'd have to sort of pay attention to. What is interesting, so the figure here, it's showing you vertical wind shear as a function of height. And notice that there is considerable wind shear, at least from sort of above 900 hectopascals, relatively little coming towards the surface, but still a decent amount of vertical wind shear. One thing that is interesting is that tornadoes tend to happen mostly in the right quadrant of the tropical cyclone. This has to do with the dynamics of the storm itself, of the cyclone itself, and we'll not sort of get into the detail of that. But yeah, this is something that as forecasters you should sort of pay attention to. That when the tropical cyclone is approaching, that area could lead to tornadoes. And so Lane could have been a big risk for all of us because it was approaching from the south. And so we would have been, if it had maintained its intensity, we would have been in the right quadrant at some point. Maybe Hawaii Island more than Oahu and Maui and Kauai, but still. The intensities are not as strong as the intensities that you could find on the mainland, but still you could have, EF2 tornadoes, which would be enough to destroy our houses here, for example. So, still something to look out for. This is some stats on sort of the hurricanes with and without tornadoes. Now, let me drink. And it's excuse me, just to reiterate that the importance of surface winds in the generation of tornadoes. Notice how the hurricanes that did develop tornadoes in the period between 1948 and 1972, they do have pretty sustained surface winds compared to those who didn't develop tornadoes. Okay, now another beautiful severe weather phenomenon that I wanted to talk to you about is dust storms. Now, why would a dust storm be considered a severe weather phenomenon? Well, after all, it's not like it's raining, balls of ice from the sky. It's not like there's a wind that's like sucking you away from the surface. Well, there are regions in the world where the wind can be so strong to completely block your visibility. It would be like extremely thick fog that is blown against you. Okay. And so actually, it could cause damage to property. It could cause damage, depending on the severity of the wind. It could cause damage because of the delays in transportation that the dust storm would cause. Okay, dust storms typically develop in the cool season, and they happen whenever there's sort of a trough that digs through in Africa. And whenever there are really strong gusts at the surface, that they could lift a lot of dust, the gusts lifting the dust, and then they can generate these really big snowstorms. The season where these typically happen is called the Harmattan, which is a particular season in African climate that is characterized by these kinds of weather patterns. Essentially, what happens during these events is that there's an upper level trough that creates a surge in pressure at the surface, and this accelerates winds that loft the dust. Okay. This figure here shows for a particular example. This shows the surge in pressure that was caused by one of these events. Africa is a region. Well, not Africa. Pardon me. The Sahara region is a region where you could imagine it's very easy to find dust storms, but these could also happen in other regions in the world. The Arabian Peninsula is another region where you can have really strong dust storms. It's a really hard word to say, but also in smaller parts, in desert places like Arizona, for example, you could have things like that. Nomenclature detail, these storms are also known as haboobs, Haboobs, I think. Finally, let's come closer to Hawaii again, and let's talk about trade winds. Let's talk trade winds. Now, I don't know if you've realized that by now, but trade winds are these, beautiful winds that are super nice on your skin. It's, they make you feel great, and we all miss them when they go away in summer when the high pressure is not as strong as we would like it to be. But there can be times when trade winds actually have, they pick up an incredible speed. And so we talk about damaging trade winds in these times. Well, essentially, let's look at the graph on this slide. This shows wind speed for a few days in December 1978. Notice how, unfortunately, there's no scale. I believe the vertical direction is the unit is in knots. And notice that there are times during those days when the trade winds have a velocity that is a speed that is higher than sort of the hurricane force winds. Okay. These can definitely be exacerbated by events, by things like orography, for example, that could accelerate winds. And they can also cause a tremendous amount of damage to the property, but also to life. They could be a cause for loss of life. This is an example of sort of a typical pattern, if you will. What happens usually is that these events take place near the exit of the region, particularly of the jet. In particular, in the right quadrant near the jet exit. If the conditions are ripe, near the right quadrant, the right quadrant exit of the jet can increase surface pressure at the surface, and this can cause the dramatic pressure surge can cause really, really strong winds near the surface. This is sort of more details of that particular event that we were looking at. And if we focus on the left part of the figure, this is showing in bold colors, this is showing isotax. And so you're at 250 millibars. And so here you're seeing the jet. And the grayish area is sea level pressure. Notice that near the Hawaiian Islands, there is a little bit of high pressure. But as the jet comes by and as the right quadrant near the exit approaches, the high pressure suddenly increases, and it increases dramatically in a very short amount of time. Given how close the isobars are, you could imagine really, really strong wind speed near the surface. In terms of the statistics, these events are kind of seasonal, and there is a clear peak during the winter months. As you can see, this is statistics that was done over a couple of decades. There is less severe trade winds during summer, but during winter, where the jet is kind of closer to us, these can be pretty frequent. There's also some kind of decadal, interannual variability, but also the counts are pretty low to make some decent statistics. I mean, it's like one event per year, 1, 2, 3 events per year. It's really hard to do decent statistics when you have 1 or 2 events. Statistics typically require a relatively large numbers. This is again sort of it's showing the sort of the patterns that we were looking at for the event that we were considering before. Again, you can see sort of the surface high intensifying as the days progress. You start like 3 days in advance, top left, and then 2 days, top right. Bottom left is 1 day, and bottom right is the day that you have the really, really strong winds. And in terms of the sort of the characteristics of these events, you have typically a pretty, sort of a relatively slow build up, and slow meaning that takes place, like over a few days. So 2 days before the event, you have an increase. You start to have a build up in trade winds, and then you have a decrease that again is over the order of a few meters, a few days. The geopotential height anomaly also kind of varies. The strongest change in the geopotential height anomaly happens at about 150 millibar. Typically have cold advection between 250 and 100 millibar, as we can see here. This is temperature anomaly at different pressure levels. There is some warm anomaly and near the surface, but in the upper regions of the atmosphere, you typically have cold advection. Okay, so this concludes what I had to say about severe weather in the tropics. It's not much, and partially because very little has been done in terms of research on severe weather in the tropics. There are still many questions that are left to be understood, although these questions are equally as important, I would argue, as those regarding severe weather in the mid-latitudes. Severe weather is severe no matter where you are, and there are many people living in the tropics. And so it's really important that we keep advancing research and our forecasting ability. So this pretty much concludes also all I had to say for this class. It's been a great pleasure to teach all of you. I feel really sad that unfortunately the last few classes could not be done in person, and I didn't have a chance to see you guys, to say goodbye to all of you. This is obviously not goodbye. It's just goodbye for now. I hope that you are staying healthy until we'll meet again. I hope you'll be healthy. I hope your families will be healthy. Obviously, our communications will continue because, well, you guys still have to take the final quiz and I have to grade you and so forth. And so it's not like I'm going to, disappear in thin air. So I'm always going to be here for you guys, particularly the next few weeks. And we will be communicating again. Hopefully I'll see you again soon in person when, times will be a little bit better and it'll be, like things will not be as wild as they are now. As usual, if you have any questions, please feel free to get in touch with me. If there was anything that was not clear, shoot me an email at any time. Call me, Skype me, whatever. If there are some topics that you'd like to keep talking about, even beyond ATMO 412, I would be more than happy to discuss with you about everything, really. All right. Well, with this, thank you so much for listening, and let me know if you have questions.